other problem you noted on the diagram? We have two long, straight, current-carrying wires, A and B. And we're asked to find the magnetic force on wire A due to wire B. Now, the key to doing these magnetic force problems is being aware of what you don't care about, okay? Both of those wires create a magnetic field. We don't care. It's B pushing on A that we care about. A doesn't push on itself, so I'm looking for the magnetic field caused by B, the pusher. Now the magnetic field due to B, by right-hand rule number 2, it's circles going around that wire. And those B field lines come out of the top and go in at the bottom. Okay, if you don't know how to use right-hand rule number 2, you need to figure that out before the final. Okay, so if I'm looking down here, I do it like that. If I'm looking up there, I do it like that. Okay? Now again, I know what the field lines due to wire B look like everywhere. But what I care about is what they look like over here where they're doing the pushing. They would be out of the page and into the page. So these would be the B field due to wire B. The B field due to wire B. Now that I have the B field that's doing the pushing, I get the push by right-hand rule number 1. Right-hand rule number 1 is the only one that gives me the force, the push. Since the B field is pointing a different direction in these two regions, I'm going to treat the two separately. Let's look up here above wire B. I have a flow of current up towards the ceiling in a B field that's out towards you. That's going to give me a magnetic force to the right. Now let's do the same thing down in this region here. The current is still going up towards the ceiling. I turn my wrist so I can wave in away from you, the B field's away from you, and I get a magnetic force to the left. So what I get by symmetry is zero net force, but a non-zero torque. This is going to try to cause wire A to rotate clockwise until it lines up with B. Remember, we found that two wires in the same direction, carrying current in the same direction, attracted each other. So now these wires are going to first of all try to get in the same direction and then attract each other. Question?
Are the magnetic forces, the magnitudes, are they different as you go up and down A? Are they
Yes.
more powerful close to B?
They depend on the strength of B, and remember we found that the strength of a magnetic field got weaker as you went further away from the wire. Twice as far, half as strong. So this magnetic force would be weaker than that one, and this one would be weaker than that one. And likewise, down here. Excellent question, thank you. Other questions? Okay. Let's review a little bit. Suppose I have two current loops carrying conventional current in the directions shown. If I were to ask you for the direction of the magnetic force on the loop on the right, how is the loop on the right being pushed or pulled? Which of those would it be with your clicker that you've just registered? Okay, last call, get it done. Okay. Let's do this together. Problems involving loops, I told you, are very, very hard, unless you replace each current loop with a bar magnet and go back to the third grade. Okay? So let's use right-hand rule number 3 to replace this loop with a bar magnet. My thumb of my right hand, if I curl my fingers in the direction of the current, my thumb points in the direction of the north side of that loop. I do the same thing with the other loop. Now, imagine you're in your third grade class. You have 2 bar magnets. You set them down on the table in front of you like this. What do you expect to happen? Yeah, they're going to come together. That means that the force acting on the right loop would be to the left. So the correct answer was to the left. To the left. Check if your neighbor did that. If not, you know what to do.
Evil eyes.
Oh, goodness. Going crazy.
Okay. Let's try another one. I have this bar magnet that's free to rotate about the orange dot in the center. Anytime you have a bar magnet free to rotate, think of that as a compass needle and put a little arrowhead on the north-seeking pole of that compass needle. Now, will that magnet pivot clockwise or counterclockwise? Your choices are clockwise, counterclockwise, or I don't know. Okay, the correct answer is counterclockwise. Again, if we use right-hand rule number 3, the current in this loop is going away from me at the top and towards me at the bottom. My right thumb is pointing towards your left, and that's not only going to point to the north side of that loop, it's also going to point the direction that the field lines are going through the loop. Okay? Those are the field lines, or the field vectors, rather, excuse me, that you would get with a little bar magnet. Now, the real bar magnet acts like a compass needle and lines up with that magnetic field. So it rotates a quarter turn counterclockwise. Questions on that? Okay, let's talk about electric motors. Most of the appliances in your kitchen have some sort of an electric motor. And these motors are very, very simple. All you have is a current carrying coil that's free to rotate. Okay? Now, if the current in that coil is coming towards you at the top and away from you at the bottom, that's going to give you a dipole that is pointing like that red arrow. Now, think of this coil as a bar magnet that's free to rotate. Well, a bar magnet that's free to rotate is just a compass needle. And it's going to line up with this external magnetic field that is somehow created pointing towards the open door. Now, that coil is going to line up and stop. And that's not a very effective motor. You know, if it just turned a little bit and stopped, you'd call that broken. What happens in a motor is when it gets lined up, we magically switch the direction of the current. Okay? Watch what happens to this current line here. It's going away from you. As soon as it lines up, we magically switch the direction of the current. That switches the direction of the dipole, and now that little compass needle's not lined up anymore. And so it keeps rotating to line that up. As soon as it gets lined up, we again magically switch the direction of that current so that it keeps on going. Now, the only complicated part of a motor, electric motor, is how to magically switch that current direction. And we do that with commutators. Lousy commutator. Okay. That's what we had in the Cold War, commutator. Okay. This is the commutator here. They're sometimes called bushings, brushes, different names for them, but essentially it's just a lead that's connected to the positive terminal of the battery. And when this coil rotates around, this side of the coil is touching the lead for half a turn. And then, when it turns half a turn, this side of the coil will be touching the lead that goes to the positive. And so, every half turn, I'm going to reverse the current through the loop. And we set it up so that that's just at the right time to keep my dipole, my little compass needle, always needing to line up. Now I have here an electric motor, a very simple one. You're going to make an electric motor, not this week, but next week in tutorial. Even simpler than this. Now that last tutorial next week has no homework. Yeah, I'm sorry. That means that it's all attendance. 15 points for showing up, 0 if you don't. So don't miss that next tutorial. Now you'll notice in this simple motor that there are two coils. There's one coil that's fixed that can't turn, and another coil that's free to rotate. Now we use this coil down here to generate a magnetic field that's constant, that's always pointing towards you. I turn on this battery, and essentially this field is magnetizing these two arms, so that this north pole and this south pole have a field pointing towards you. Now this second coil can turn in that field. And when I turn on this battery, I will get a current and that causes it to be pushed, always lining up with this field here. Now, how do I switch the current back and forth? Well, those of you in the back are going to have a hard time seeing this, but I've got these little metal bars here. And the leads to my coil are brought into this collar. But the collar is not all the way around the axle. It's two collars, two half collars that are separated. You see that line of black there and that line of black there? I've got two half collars like this. And as it turns around, each half turn, I have a different half collar touching this lead here that goes to the positive lead of the battery. Now, what would happen if I switch the leads? With the leads like this, it goes around that way. The more current, the faster it goes. Let's switch those leads. Now it goes the other way, and the more current, the faster it goes. Okay. See if your neighbor understands motors. Okay. Let's talk about Faraday's Law. You remember that we were able to make a wire jump just by putting a current through the wire in the right direction in a magnetic field. And this was the principle that drives our stereo speakers as well as anything that runs on electricity and has a motor in it. Now, in this case here, we had a magnetic field that was pointing towards the open door. We used a battery to drive current through the wire in a direction towards you, and that gave me a magnetic force, VB, up. And that's what caused it to jump. Now, we're going to do something very, very different. We are going to remove the battery and we are going to take the leads of this wire and we are going to hook them to this ammeter. And what I'm going to do now is I'm going to take this wire. There's no battery, nothing to drive current through this wire. But as I take this wire and push it between the poles of that magnet, suddenly you see current. Well, you don't, because you're in the wrong seats. Okay. Did you people over here see it? Okay. Now, how do I explain that? Well, if I think of that wire as a plastic tube that contains positive charges that are free to move along the tube. Now we know it's really electrons that are free to move along the tube, but we played this game before. The electrons going one way is no different than positive charges going the other way. And we always deal with conventional current. Now if I take this wire and I thrust it down between the poles of this magnet, when I move the wire down, I'm taking all of these charges, positive charges, and moving them down. Okay? I'm giving them each a motion down in a magnetic field. Now if I look at the magnetic force that produces, I reach down in the direction of the motion, I turn my wrist so that I can wave in the direction of the open door. That gives me a force towards you. And the charges are free to move that way. They're pushed that way, so they go that way. That creates the current in the wire that the ammeter is picking up. Okay? Now, we call this magnetic induction, and this is the way that all of our cities are lit up. If you go looking for the source of all of these lights, you're not going to find a great big warehouse filled with batteries. It doesn't exist. what you find is a hydroelectric dam where you have this going on, magnetic induction. This is also the secret to why they had so many electric machines on Gilligan's Island. Gilligan was always producing electric current for, well, really all of them, but mostly for Ginger and Marianne, right? Okay. Do you have any idea what I'm talking about? It was a 3-hour cruise, okay? When I was alive, all human males were divided up into 2 groups. The group that were interested in Ginger and the group that were interested in Marianne. And we were that simple that we thought that everything could be divided up into those 2 groups.
Which group were you?
Yeah.
Marianne. Ginger is just too flashy. Okay, let's not talk about this. Okay. This principle of magnetic induction was first taught by Michael Faraday. Michael Faraday was described by one of his colleagues as a man almost entirely innocent. Now I would ask you, is that a man that looks almost entirely innocent?
Yes.
No. Let me finish the quote. Michael Faraday was a man almost entirely innocent of the laws of mathematics. How would you like it if your friend said things like that at your funeral? He's totally ignorant. Couldn't do math. And yet, that was true. Michael Faraday wasn't good at math. And yet he gave us some of the most powerful physics that we know today. And that's because he could visualize magnetic field lines. To him, they were real. And because of that, he could see things that others couldn't see. Now, we're going to do some experiments. If I want to get current going around a loop, a copper loop, one way is to hook it to a battery. And that would get current going around that loop. Michael Faraday said, you don't need no stinking battery. All you got to do, hook that up to an ammeter. He says, all you've got to do is take a permanent magnet and move it towards your loop or away from your loop. Now, you seeing the current that's being generated there? Now watch what happens when I put it in there and park it. Very powerful magnet right in the middle of the loop. Do I have any current?
I don't know.
It says 0. Do I have any current?
No.
No, okay. When I pull it out, I get it. When I put it in, I get it. Now, these people could say they don't know because they're seeing my backside. Okay? And when I park it there, 0. What? Don't make me come over there. Okay. Now, let's see if we can understand this. We call it induced current, meaning I can't see the magical battery that's causing this current to flow. Okay, induced current. Now, I hope everyone can see that there's no difference between bringing the magnet towards a loop or holding the loop still and bringing... Let me think that through. There's no difference between bringing the magnet towards a loop or bringing the loop towards the magnet. Did I get it right?
Yeah.
Good. Okay, I need a helper here. Would you help me? Come on down, please. You're just going to hold the magnet. It's not a hard job. Okay, you're just going to hold that. Okay, and here's the loop. Okay. Got your name? Amanda is holding the south pole towards me, and as I push this copper loop towards the south pole, think of this as a hollow plastic loop with charge carriers, positive charge carriers. I am moving not only the loop towards the south pole, but all of these charge carriers in the loop towards the south pole. Now, that's going to give them all the velocity towards Amanda in a magnetic field that is pointing towards the South Pole that she's holding. Now, because those two directions are not the same, I'm going to get a magnetic force. Let's look at a charge up here at the top. It's moving towards Amanda in a field towards that South Pole. It's going to be magnetically pushed away from you. Okay? Let's look at a charge down here. It's going to be moving towards Amanda in a field that's towards that South Pole. That's going to give a magnetic force towards you. Okay? Now, that's going to cause current to rotate away from you at the top, towards you at the bottom, around this way, induced current. Now, I chose the top and the bottom. I could choose any point. If I choose this point here, towards Amanda, towards the South Pole, up. If I chose here, towards Amanda, towards the South Pole, down. So here it's away from you, here it's down, here it's towards you, here it's up. It goes around. Thank you, Amanda. I appreciate it. Okay. Now, does there have to be motion in order for this induced current to exist? Well, Faraday taught us that it didn't. And he gave us this example. If you have two coils, he called this one a primary coil and the one hooked to the ammeter the secondary coil. If you put them next to each other, what you find, let's show these people first, they paid more money. When you connect the battery to the primary, suddenly you get an induced current in the secondary. But then it goes away until I disconnect the primary. And then you get an induced current the opposite direction for a short time. So it's only when I connect and when I disconnect. Okay? When I connect and disconnect. If I leave it connected, that induced current goes to zero. Okay, let's show the cheap seats. So when I connect it, there's an induced current. When I disconnect it, there's an induced current. If I leave it connected, that induced current goes to zero. It's only when I'm disconnecting it or connecting it that I get the current. Okay? So the answer, Faraday taught us, is no. Here's a summary of that little experiment. You close the switch. That gives you current in the primary as long as the switch is closed. We immediately see an induced current in the secondary that quickly goes away, even though I've still got current in the primary. And there's no induced current until I change that current in the primary by disconnecting it. And then I get a brief kind of a spurt of induced current the opposite direction from what it originally was. And then it goes away. So the answer seems to be no. These coils were not moving relative to each other. Okay? Now, what about this? Maybe the B field has to change. Think about that for a minute. With our first experiment, we were taking this permanent magnet and we were changing the magnetic field strength inside that copper loop. It's very weak when it's over here. It's very strong when I put it in the loop. And then I make it weak again. So I'm changing the field strength inside the loop from weak to strong to weak again, and that generates this current. Likewise, if I look at the second experiment, this primary coil becomes a magnet whenever I connect it to the battery. A loop carrying current is a bar magnet. So connecting this is like bringing a magnet nearby, right? And disconnecting it is like bringing the magnet away. I'm changing the strength of the magnetic field through this secondary loop either way. Well, Faraday came up with a thought experiment. He said, suppose you had two copper rails and you hook those copper rails to the leads, the terminals, of a bulb. And then you have a copper bar that's free to ride on those rails. Now, in between the rails, you somehow set up a magnetic field. What can you tell me about that magnetic field just looking at those magnetic field lines?
Uniform?
It's what?
Uniform?
It's uniform. They're always spaced the same distance apart. That means whatever magnetic field strength I have in Tesla here, I got the same magnetic field strength in Tesla there. You also know the field is pointing away from you. Now think of this experiment as something you're looking down on, as if you're just having an out-of-body experience and you're looking down on the experiment there. Now, what Faraday said was, take that copper bar and slide it along the rails. As soon as you slide the copper bar, oh, that's hot. Don't tell anybody. I left it on. As soon as you slide the copper bar, you're also sliding all of those positive charges, the charge carriers, that way in a magnetic field that's that way. Well, that's going to give me a magnetic force on those charge carriers. That's the velocity. That's the B field. The magnetic force would be up. Now, because the charges are free to move up, they do. And that gives me an electric current. But I can't have an electric current there without having an electric current everywhere in that loop. And suddenly the bulb lights. Okay? Now here's the thing. Did I change the strength of the magnetic field inside my copper loop? No, it's the same strength that it was always in Tesla. What I did change was the number of field lines in the loop. And now let's go back and think of the other experiments. And this is where Faraday was a genius. When he saw this bar magnet, he didn't just see the bar magnet. He saw the field lines coming out of the North Pole. And they came out and they spread apart. Okay? Now think of that. Try to be Faraday and think of those field lines coming out and spreading out. I'm holding that field line, pointing it towards that loop over there. How many of the field lines are going through that loop? Not maybe, not many, maybe one. But as I get this closer, those field lines that are spreading out, more of them are getting through the loop. And now all of them are getting through the loop. I'm changing the number of field lines going through that loop. Just like I'm changing the number of field lines through that loop. Likewise, with our second experiment, when I connect this to the battery, I turn the primary into a bar magnet. I change the number of field lines through the loop from none when it's not connected to lots when it's connected. In every case, we're changing the number of field lines. Now, we call that the magnetic flux to try to scare you. And we give it a scary Greek symbol, phi, again to try to scare you. The more scared you are of science, the more powerful we as scientists are. That's not true. It turns out the more scared the populace is of science, the weaker and less influence that we have. But anyway, magnetic flux is nothing more or less than the number of field lines. And when we change the number of field lines through a copper loop, it sets up an EMF. Do you remember what an EMF is? A battery, an electromagnetic force, but it's really just a battery, an invisible battery that drives this induced current. Okay? Now, the number of field lines is what we call the magnetic flux. And to calculate it, we multiply the magnetic field strength in Tesla times the area in meters squared. Let me see if I can motivate that formula. We use magnetic field lines to represent where the magnetic field was strong and where it was weak. It was the density of field lines that told us the strength of the magnetic field. So that means that the magnetic field strength was proportional to the number of field lines that fit through a perpendicular area. If I had some area, let's say it was a circle like this, the more field lines I could fit through that area, the closer they would be together and the stronger the magnetic field. Now if I multiply both sides of this equation by area, the area cancels out over here, and what I get is a measure of the number of field lines. This quantity, B times A, is proportional to the number of field lines. And when I change that through a loop, I generate this invisible battery. Now, I'm going to do a demo that requires that I turn off the lights. What I have here is a strong horseshoe magnet, and actually, I don't want to ruin your camera. I have a coil that is hooked to a flashbulb. Now, a flashbulb, when I was alive, is how we took flash pictures. You would have a cube that you would put on top of your camera, and each cube had 4 of these little bulbs in it. And each bulb has some magnesium filings in it. When it was time to take the picture, you push the button connecting the camera's battery to this little cube. And that would cause this thing to flash. Now, what I'm going to do, Faraday teaches us we don't need the battery. I'm just going to change the number of field lines through that coil. And let me turn off the lights first. And okay, watch carefully. What did you see? Nothing, because I lied to you. I said that changing the number of field lines was what made the battery. It was indeed how quickly you change the field lines. Do you want to see that again? Yeah, just close your eyes. You'll see it all day. Actually, I can show you that again. We ran out of these little bulbs, and you couldn't find them on eBay, and so we couldn't do this demo anymore. So I searched all over Montana, all these little shops, and I found a little photography shop. The guy had been just throwing all of his bulbs in a couple of big boxes in the back room. He didn't know what he was going to do with them. He just didn't want to throw them away. No one used them anymore. And so I found him, and I found these boxes, and the university bought all the boxes. So we've got these now. And this big one is going to make a much bigger flash. It's not going to blind you. We tested it on grad students. Okay, it's a big blue one. So, let's do it right. I love physics. Physics is so much fun. Okay, if I put it through the between the poles slowly, I get nothing. If I take it out quickly, I get nothing. Come on. Oh, yeah, laugh at me. Blind you, Now,
There's still purple in my eyeball.
my eyeballs are burning. Okay, here's the piece that I wasn't telling you about. It's not just how much you change the flux or the number of field lines through the loop. It's how quickly you do it. How many field lines you change per second. Now this is Faraday's law, almost, okay? That EMF on the left is the invisible battery that drives this induced current. The part that's missing is the most famous minus sign in all of physics. It has its own name. It's called Lenzs Law. It's going to be the topic of this week's tutorial and the topic of Wednesday's lecture. You are going to find that that minus sign means fight. The EMF will be set up always, always, always to fight any change in magnetic flux through a loop. Okay? Now, there's one big idea that we kind of skirted, and that is that if I take a bulb and connect it to only 2 loops instead of 100 loops, I can do this as quick as I want. I'm never gonna flash that. It depends on how many loops you have in your coil. If I change the number of field lines through this loop from 0 to 4, okay, there's 4. I send 4 through there. I'm sending those 4 through the first loop and the second loop. I count that as 8 field lines that I've changed. But here, if I send 4 field lines through, I'm sending it through 100 loops, and that's changing by 100 field lines. So the number of loops matter. We're going to have to modify our equation for flux. It's not B field times A, it's National Basketball Association. Did you remember that? National Basketball Association. Now, suppose you were given the job to protect the border of America. You were protecting the border with Canada. And what are you laughing about? You're trying to keep those crafty Canadians from trying to sneak in. Can anyone see my bar magnet? Over here. We're trying to keep those Canadians from sneaking in magnets. They're always doing that. So one way you could do that is you could set up a door, buy a door at Lowe's, wrap wire around it and hook it up to an ammeter. And whenever those crafty Canadians tried to go through that door, you got them. Now the hard job, the really hard job, is protecting Canada from Americans, because we're a violent people. We try to bring knives and guns and bad things across the border. Now, this will represent a gun. Suppose an American was coming into Canada with a gun. That's just not going to trip the detector. So how could we magnetize this gun so it would trip our detector? Yeah, one thing we could do is we could put a greeter at the border and say, "Excuse me, sir and or madam, could I please see your weapons?" And then just put a magnet on them. That's gonna keep the dumb criminals out. Okay? But another way would be to set up another coil around that door and hook that second coil up to a battery. And then, when they tried to sneak that gun through the first coil, it'd get magnetized. When it went through the second coil, it would trip the switch. Now, did you see that over there? Sorry about that. Now, can you think of a way that you could still get that gun on the plane or through the border? Think of the flashbulb.
Walk slowly.
Walk slowly. It's the old ladies that are packing. Yeah. You gotta throw those old ladies through the door. Yeah, you do. Now, folks, before any of you go down to the airport and try to get through that detector with your gun, believe me, their system doesn't work on DC, it works on AC. You're not going to be able to walk slow enough to get through there. You're going to get a free colonoscopy. Okay, we'll pick this up on Wednesday, folks.
Go farther.